Hello, my name's Stephen. I'm one of the lecturers in the Department of Mathematics at the University of York. And today I'm going to talk to you for about 20 minutes about the mathematics of card shuffling. This may be something that you've not really considered before, how maths and card shuffling can go together. But it's something that's quite close to some of the research that I do when I'm not teaching our undergraduate students. And I hope that over the course of the next 20 minutes or so, I can give you an understanding of why I think this is a particularly interesting and exciting area of mathematics. Okay, so the question that we're going to consider in this talk is the following. How many shuffles does it take to randomize a deck of n cards? So here n is the number of cards we're considering. That could be any number. This question makes sense for any number of cards really. But if you'd like to think about a standard pack of playing cards, you might like to think about just n being 52 for the purposes of this talk. So if you look at this question, you might think, well, that sounds reasonable. How many shuffles does it take? But then if you start thinking about it a bit more carefully, you might think, well, what exactly does he actually mean? This question is not very well formed. And as mathematicians, we really like to have very definite, carefully worded questions so that we know that we're giving careful, considered answers to them. So in particular, you might be thinking to yourself, well, what do I mean by shuffle? If I don't describe what I mean by a card shuffle, you and I might have very different ideas of how we're shuffling the cards, and then we're going to have very different answers. So I need to tell you what I mean by a card shuffle. Secondly, you might think, well, what does he mean by the word random? Randomize a deck of cards. People have very different ideas about what randomness really means. And so I need to tell you what I mean by random so that you're going to have a chance of understanding what I'm talking about. The third thing you might be thinking is, well, why do I care? Okay, why should people care about this? I'm going to tell you a bit about why I care about it and why other people care about it. And then it's up to you to decide whether or not you think this is something worth caring about as well. So 3 sub-questions to answer as we go. The first of these is, what do we mean by shuffle? So there are lots of different ways in which we could shuffle a pack of cards. I'm just going to give you a few possibilities here. So the first one I'm going to mention is the riffle shuffle. So here I take my deck of cards. Here I have a standard pack of playing cards. Okay, and I riffle shuffle it as follows. So I'm going to try to do this without throwing the cards everywhere. I take the pack and I split it into 2 roughly equal packets like this, and then I riffle them together like that, and then push the pack back together like that. That's a single riffle shuffle. Okay, so I've got a little animation of doing this, which is a bit better than me doing it in real life, perhaps. So here I split the pack into 2, slide the top off, and then riffle them down in amongst the other cards and push them back together. I could do an overhand shuffle. Here I take all the cards in one hand like this, and I drop some into my other hand. Okay, and I keep going, so some cards slide off each time. I keep doing that until all the cards have been transferred from the starting hand into the other hand. That's a single overhand shuffle. Again, I have a little animation of this. So a few cards drop into the other hand, and some more. That's a single overhand shuffle. So these 2 shuffles are used by people when they're playing cards all the time. 2 shuffles which aren't used so much in real life are the top to random shuffle. Here I just do what it says. I take the top card off and I stick it somewhere at random. And then I repeat, take the next card off, stick it somewhere at random. And you keep doing this over and over again. And the transposition shuffle. This one is very close to my heart. It's similar, related to a lot of the research I've done. So here for the transposition shuffle, you think about laying the cards out in front of you on a table. With your left hand, you choose one of the cards at random. With your right hand, you choose a card at random, and then you swap the 2 cards that you find that you've touched. Okay, so here we go. I choose 2 cards at random. Here I've labelled them with different colours, and then I swap them over. I could do it again, and you keep repeating this over and over again. So as I said, some of these model real-life card shuffles, the first 2, for example. The others aren't what people use when they're playing cards. You'd look quite odd if you started shuffling cards doing a top to random shuffle if you were playing them, but they are nice mathematical models. The analysis often turns out to be particularly nice, and these also have connections to other real life problems. So there are reasons to be interested in the maths behind these as well. Okay, so there are different ways of shuffling cards. Suppose we've chosen a method that we want to study. The next question was, what do you mean by random? I need to explain that. Okay, so when I take my pack of cards and think like this, what I have is a set of n different objects. Each card has a different label, and they're in some order. Now, in maths, the word we use for describing an order of different objects is a permutation. Okay, so the total number of possible orders, or the total number of permutations, is, as you'll see during the course of A-level studies, if you're doing those, is this number n factorial, which we write shorthand as n exclamation mark, which just stands for this number we get by taking n and multiplying it by n minus 1, and then by n minus 2, and so on, all the way down to 1. So, for example, with just 3 cards, n is 3, I should have 3 times 2 times 1, which is 6 different permutations. And with 6, I can write them all out quite easily. There they are on the screen. But this number n factorial grows very quickly as n gets bigger. So you can calculate a few quite easily in your head, right? So 4 factorial will be 4 times 3 times 2 times 1. That's 24. 5 factorial, I can multiply by 5. Now I get 120. 6 factorial is 720. 7 factorial is starting to get a bit difficult already. Okay, but you can see it's getting big very quickly. And if I want to think about this pack of playing cards with 52 cards in it, if I work out 52 factorial on a computer, it comes out to be about 8 times 10 to the power 67. So that's 8 with about 67 zeros after it. And that number is huge. Right? It's so big that the best way I have of describing it is as follows. This number is bigger than the number of atoms in the Earth. Okay, so what you could do is you could take, in theory, every atom of the Earth and label that atom with a different ordering of the cards. Okay, because there are more permutations than the number of atoms on Earth. Suppose you could do that. Okay, so you attach to each atom a label corresponding to one ordering of the pack of 52 cards. That doesn't use up all of the possible orderings, so then rub them out and relabel. Okay, and you attach now a different set of orderings to all of the atoms in the Earth. That still doesn't use them all up. Rub them out, do it again. And suppose you've been doing that, rubbing them out, labeling, rubbing them out, relabeling. If you do that once every second, then how long would it take you to actually use up all of the orderings? Well, actually, you could have been doing this since the time of the Big Bang. If you'd started doing this at the time of the Big Bang, labeling atoms of the Earth, I don't know if that even makes sense to talk about atoms of the Earth at the time of the Big Bang, but labeling all the atoms of the Earth, rubbing them out, relabeling, doing that once per second. If you've been doing that since the time of the Big Bang, you would just about now have finished writing out every single possible ordering of a deck of 52 cards. Okay? So the number of permutations, this 52 factorial, is about the same as the number of atoms in the Earth multiplied by the number of seconds since the Big Bang. So it's huge. Right? Nobody has ever written out every single possible ordering of a pack of 52 playing cards. It's just too big. But it is finite, and I know exactly how many different permutations there are. So what I'm going to mean by random is that for a well-shuffled deck, when I want to say my deck is now randomized, what I want is that each of those possible orders is approximately equally likely. That's what you want if you're playing cards, right? You want each of the possible orders to be approximately equally likely so that it's not more likely that you have a king on the top of the pack or a 3 on the top of the pack, for example. So I've got some idea of what I mean by my deck being randomized. It's in this sort of ideal state where each order is approximately equally likely. We're going to start off with a pack of cards which is in some known order. We then start applying our shuffle, whichever shuffle it is we want to study. And what we want to do is to keep applying the shuffle until we get close to this ideal state in which each of the orders is equally likely. But if you're listening to the words I'm using now, I've started to talk about how close to something we are. And that means there's an idea of distance going on. So we need some way of measuring the distance of how far the deck is from this randomized state. Now in maths, we have lots of different ways of measuring distance, some of which are more useful in some situations than others. Okay, and I don't have time to talk about how we do that properly in this case here, but what I want to do is to give you an idea of a way of measuring a distance that's phrased in terms of a game. So here's the possible game, which you can try at home, but I suggest you only really do it if you're very bored. So here's the game. You're going to go through the deck of cards and you're going to guess the values of each card sequentially, okay, and see how many you get right. So if I was doing this in a lecture theatre, I'd get people to try and shout out cards and guess the value of the top card. I'm recording this from home. I'm not in a lecture theatre, so I'm going to play your part and call out a card. I honestly don't know what this card is, so let's see what happens. I'm going to say the top card is the 3 of clubs. So let's turn it over. It was the 7 of spades. Okay, so no points for me so far. And then I go on to the next card. Okay, now, again, I've got a lot of possibilities, but I know it's not the 7 of spades because we just saw that one. So I'm going to say it's the 5 of diamonds. 5 of spades. Still wrong. Okay, and I could carry on playing this, okay, say if I was very bored, and see how many I get right as I work my way through the pack. And it should get slightly easier to guess the cards correctly as I work my way through and I get more information about what's happened so far. So we could say if I were to play this game multiple times now, how many cards would I expect to get right on average? So that's going to depend on how well shuffled the cards are. Right? So if I start off with my cards in a known order, I've done 0 shuffles, I will get them all right because I know the order. Okay, so after 0 shuffles with a 52 card deck, I would get all 52 correct. If my pack is in this ideal state where every possible order is equally likely, how many would I expect to get right there? Well, the first card I'm not going to get right very often, right? Because there are 52 possibilities. Each card is equally likely to be on the top, so I'd expect to get that first card right about 1 in 52 times I play the game. The second card that I've looked at was slightly simpler because there are only now 51 different possibilities, each equally likely. Okay, so once I know what that top card is, I'd expect to get the second card right about 1 in every 51 times I play the game. And you can see how this pattern's going to go on. When I get down to the last 2 cards, okay, there are only 2 possibilities left, so I'd expect to get the penultimate card correct about half the time I play, and I will always get the last card correct. So, putting this into the sum, how many would I expect to get right altogether? I expect to get about 1 in 52, and then 1 in 51, and 1 in 50. You add these things up, okay, down to a half plus 1, and I see that that's about 4.5. So if my pack was truly random with every possible order being equally likely, I would expect to get about 4.5 correct in playing this game. So the picture you should have in your mind now is the following, right? If I'm starting with my pack in an order I know, and I would expect to get 52 cards correct. I get them all right. Then if I do more and more shuffles, I would expect the number I could get right to drop as I do more and more shuffles. And then if I do enough, I'm just going to get close to this value of about 4.5, which is what I would expect to get right if the cards were perfectly well shuffled. Okay, so it's starting at 52, and it's going to drop and get close to 4.5 after a while. And then the question becomes, well, how many shuffles do I need to do until the number I could expect to get right on average is near 4.5, and I'm content to start playing my card game. So what's really surprising and quite exciting for mathematicians is that for many types of shuffle, there turns out to be a critical number of shuffles you should do. Like to the extent that if you do fewer shuffles, the pack is barely mixed, so you're still quite close to 52, right, that you'd expect to get right if you've done fewer than this critical number of shuffles. Okay, so this graph that I was sort of giving you an idea of with my hands a moment ago, saying it starts at 52 and then drops towards 4.5, actually stays quite close to 52 for a while until we get to this critical number of shuffles, and then it drops quite suddenly as all the sort of randomness kicks in. You get suddenly quite close to this ideal state of only being able to get to about 4.5. So all the convergence here to this ideal state happens really quite quickly. And that's what we mean by this critical number of shuffles. And that's not something that we necessarily expected to happen before people started studying these card shuffles. Okay, so it tends to be a critical number. If you do fewer shuffles, the pack is barely mixed up. But if you do more shuffles, yes, you're introducing a little bit more randomness. Okay, but it's such a small increment that you're just wasting your time. Nobody wants to play cards with you anymore. So I should tell you what this critical number is, right, for the different shuffles that we talked about at the start. So for the riffle shuffle, this is now quite well known in the sort of public domain. The number of riffle shuffles you need to do is about seven or eight, really, for a 52 card deck. That was surprising when mathematicians discovered this back in the 1990s. That made newspaper columns because people generally don't do 7 or 8 riffle shuffles when they're playing cards. And these mathematicians showed that if you're only doing 3 or 4, you're barely shuffling up the deck at all. For the top to random shuffle, remember you take the top card off the deck and insert it at random. This takes about 200 or so. It takes a long time in this shuffle to mix up the cards which are near the bottom of the deck. Okay, so these ones here tend to stay pretty close to their original relative order until you've done enough shuffles that you actually start putting cards near the bottom and pushing the bottom of the deck back up through the pack. For random transpositions, where you lay the cards out, pick 2 at random and swap them, this takes about half as many as the top to random shuffle. So intuitively, you're moving twice as many cards at the same time. It turns out to be faster. For the overhand shuffle, remember this one here that people use a lot when they're playing cards. So that's a single overhand shuffle. This one here takes thousands. Okay, but over 1,000, might be nearer 2,000. It's a lot, right? This is a really bad shuffle. The cards stay very clumpy. It really doesn't mix up the cards very well at all. Okay, so the take-home message from this talk is that if you're going to play cards in real life, you should really learn to riffle shuffle. Okay. The final thing I said I would talk about is, why do people care? So some people care about this stuff because the applications are interesting. Some people care about actually making sure that cards are well shuffled. If you play cards for a living, or you run a casino, for example, and you might be using card shuffling machines, you really want to check that these do shuffle up cards in the way you're expecting. There are some nice links to problems in other areas. So list management problems. This is a computer science type problem to do with storing files in a database and being able to access those and shuffling the order of them as people need the files. There's a nice link to that. There's a nice link to a biology problem with genetic mutations, in which parts of a chromosome in a type of fruit fly can be inverted as you go from one generation to another. So you think of the chromosome being a sort of long list of these genes, and part of it sort of being cut out and inverted, flipped over. And then what I'm doing with my hands there is sort of reminiscent of what I was doing with the transposition shuffle. I was picking 2 cards and swapping them. And it turns out that some of the maths used for studying the transposition shuffle can be used to study these genetic mutations in flies. I care about it more because the maths is interesting. Okay, this is a really nice area of maths, combining theory from quite disjoint areas. Okay, so there's probability involved, clearly, the theory of randomness. There's algebra involved. Algebra at university is a bit different to what people tend to think of it as at school level. At university, we really mean something called things like group theory and the study of symmetry. What I'm really doing, mathematically speaking, when I'm shuffling a pack of cards, is performing a random walk on the symmetric group. Okay? They're words you might not understand at the moment, but if you start on a degree in maths, you certainly will quite early. And analysis as well. So real analysis. I gave you some answers for how many shuffles it takes to randomize a deck of 52 cards. When I said it takes 7 riffle shuffles, that answer there was specific to 52 cards. But as I said at the start, this question makes sense for any number n of cards. So then we might say, well, what happens as n changes? If I double the size of my deck, I can expect it to take more shuffles to randomize the deck. But how does that number change? Does that also double with the size of the deck, or is there some other relationship going? And we can answer these questions using some theory from real analysis. So these are sort of different areas of maths, and they're all things that we start teaching students at York in the first year. Of our single subject program, you'll be learning probability, you'll be learning some algebra, you'll be learning some analysis. Okay? And what this means is that you can start learning some of the basic theory you need to understand this card shuffling problem right from the word go. And then by the time you get into your 3rd or 4th year, if you're taking a final year project, I find students each year coming to me and asking to study card shuffling because it's a nice way of using lots of different bits of maths that they've learned about over the last few years. So that's why I think it's interesting. There's some really nice areas of maths here. There are still lots of interesting questions still unanswered. Some of them I'm helping to answer as part of my research, but there are other people all around the world working on these problems. I feel quite privileged that I get to look at and try to understand these problems as part of my work. And yeah, I hope that you've also got some idea of why I find them interesting through the purpose of this talk. Thank you for letting me chat to you about it for the last 20 minutes. I hope you found it interesting.